Hello, today we're going to talk about electromagnetic waves. Remember, up to this point, we've been talking strictly about mechanical waves that travel through a medium. Electromagnetic waves travel through space. They can travel through a medium, don't get me wrong, but they don't have to have a medium, and that's what makes them a little bit different, a little bit more unique. And so, again, they do the same thing. They're carrying energy from one place to another. And they are made by vibrating electric charges that can travel through space where matter is not present. Instead of transferring energy from particle to particle, electromagnetic waves travel by transferring energy between vibrating electric fields and magnetic fields. And this is the electromagnetic spectrum. And we're going to watch a little quick video put on by NASA about them.
What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph.
Okay, I think that's enough of the movie to give you an idea of what the electromagnetic spectrum is and electromagnetic waves. So let's go on in our notes. Again, there's an electro part to this and a magnetic part to this. So electric charges are surrounded by electric fields, An electric field enables charges to exert forces on each other even when they are far apart. An electric field exists around the electric charge, and then we've got the magnets are surrounded by a magnetic field. And then what you're having here is you get both going. So you've got moving electric charges surrounded by magnetic fields. That's when you get electromagnetism, which is the basis of electromagnetic spectrum. So making electromagnetic waves, they're produced when something vibrates, an electric charge that moves back and forth. And the electric charge is in motion and it has a magnetic field around it. This magnetic field also changes as the charge vibrates. And here's a great picture of it showing the different electric magnetic fields and the direction of travel and how they do travel perpendicular to it. So here it says the wave is shown in one direction only, and all electromagnetic waves travel the same speed, which is the speed of light in the vacuum, which is 3 times 10 to the 8th meters per second, or 300,000 kilometers per second. The speed of electromagnetic waves in space is usually called the speed of light. So nothing travels faster than the speed of light. In matter, the speed of electromagnetic waves depend on the material they travel through. So here you see this is what them traveling through space. And so if we're doing a problem with an electromagnetic spectrum wave, we're going to probably use that value. Let's go through our section check. What is represented by the blue lines on this figure? That's the magnetic field lines. And then describe the major difference between electromagnetic waves and sound waves. One of the major differences is electromagnetic waves do not have to have a medium to travel through. And so you have, I'm sorry, I'm getting my phone's dinging like crazy. The major difference between electromagnetic waves and sound waves is that electromagnetic waves do not have to have a medium to travel through. Sound does. All mechanical waves have to have a medium. An electromagnetic wave is a D-transverse wave, would be the correct answer to that. Okay, the remainder of the slides are practical applications of waves. I'm going to publish the slides on Canvas, and you can look through them. This might help you get a start on the assignment today. The assignment today is for you to do how something works. And you can see I have quite a bit of information on how something works on these slides. So once you make your choice of what you want to look at more carefully, then you can use these slides to help you get a boost. And then How Stuff Works is a really great site to go visit and read. And so that's what your assignment is to really investigate electromagnetic spectrum.